You have?
Yeah.
Huh.
When we do the case
Uh-huh.
of a small interaction
Uh-huh.
in the diffusion term of the
Interaction term, yeah.
sorry,
Huh.
the small diffusion term,
Huh.
we do this perturbation analysis. We
Uh-huh.
expand as a series of perturbations in
Uh,
the nodes.
okay. So maybe in the notes part, maybe we can discuss after. Then you can show me which equations you have issue with. Okay. This is probably regarding the Van der Pol oscillator, no?
Yes.
Okay, okay. We can do it after. Okay. Other, questions from the lecture content, whatever I talked about during my lecture yesterday. So let's ask even a basic question, that how many still do not understand what synchronization is? So you all understand what do we mean by synchronization? The way we want to understand it, right? I mean, constant phase difference, etc. That is understandable? Or you want me to go over it again? Because the rest of it is algebra showing that a particular model can predict a synchronization transition. But if we don't know what we are after, then so it is okay, right? Okay. So so the setup that we had was, let me just briefly recall. We had several limit cycle oscillators. This one had frequency, angular frequency or intrinsic frequency omega 1, omega 2, omega 3, omega 4, and so on. And each one of them had dynamics of the following sort. D theta I dt equal to omega I. I have n such oscillators, n such limit cycle oscillators. N can be anything. And then there is, we argued that, okay, we want to model weak interaction between them. So the weak interaction, it has to be of the following form. J equal to 1 to n, j not equal to I of some function which is a function of the pair that I am talking about, theta I minus theta j. N is the number of oscillators. So many people had asked, or at least one person had asked me, what is N? N is the number of oscillators. N can be 2, 3, 4, 5, 7, 15, whatever. Okay. Until now everything was general. The only thing that we invoked in getting to this equation is the fact that this epsilon is a small number. Okay, it can be positive, negative, whatever. Okay, epsilon is a small number. We want weak interaction because otherwise there is no fun or nothing, so to say, surprising in studying synchrony in this system of oscillators, because if you have a very strong interaction, then obviously I mean the system would synchronize. So the question is, despite having a weak interaction in the system, does the system still like to synchronize? So this was very general. So up to this part everything is fine. Like the way we derived it, we invoked a time scale separation. We said that okay, there are these fast degrees of freedom that we are going to fast oscillations which we are going to integrate over, and then there are slow oscillations which we are going to retain, and that's how we saw that the interaction has to be of this form. So let me pause for a minute and say that the fact that this interaction is a difference of the phases of the interacting oscillators is not at all an obvious concept. I mean, there is no, since these equations are not derived from an underlying Hamiltonian, so therefore there is nothing that says that it has to be a function of the difference, but it turns out to be a function of the difference. Qij, this function is different for different pair, and well, epsilon is a small number. So Kuramoto wanted to study the simplest setting in which to do the analysis and see if you get synchronization out of it. Sorry. So he said that the first simplification pertains to the fact that let me take this function qij to be the same for every pair. So qij is some function q for all ij. It is one master function. It doesn't, you can make it complicated, but let's say this is one. And secondly, this is a periodic function of the, q is a periodic function of the argument. So he said that let me choose q to be equal to q theta, to be equal to minus sine theta, and this epsilon to be equal to some k over n, where k is a number which is larger than 0, and then the equation that he got was I just substitute these forms therein. See, this restriction j not equal to I don't have to put in here explicitly, because anyways when j is equal to I, this term is 0. So I don't have to put it by hand. This is our model. This is not the model. There is nothing called the model of synchronization. It is a possible scenario in which one can study it, and one can make life complicated by saying that, oh, but I can make this function function of the the pairs that I am talking about, and instead of taking sine theta, let me take it sine 76 theta, and so on and so forth. But nothing can be simpler than this. Okay. So this is more or less the ground level from which you can take off, and then sky is the limit. Okay. So now the question is, we want to study this model, and as I was mentioning last time, that this model on the face of it doesn't offer the possibility to be studied analytically, because what do you do with this model? Yes. This one? Yeah, because then this is sine theta I minus theta j with a minus sign, so I just flip it. Or there are many ways you can do it. What you can do is you can call it sine theta, but you take k to be negative. We will see why k is required to be positive. What happens if you take k negative, etc., etc. We'll do it. We'll see how to do it. Okay. Yeah, so on the face of it, this model doesn't offer the possibility to be solved analytically, because what do you do with it? Because these are nonlinear differential equations and there is no noise, so you cannot, this is not even a Langevin equation or a Fokker-Planck equation, so you can write down some, some Fokker-Planck equation and solve it and get to the steady state and so on. So how do we do it? So let's backtrack a little bit and study a slightly simpler model, and then we will see how a study of that simpler model allows to make some definite predictions for this model. Okay. That, by the way, is the Kuramoto model. So we will study this system. This is, of course, it is given in the notes also, and I think it is given in the appendix of the notes. So let me just follow that in the section on fixed points, because I had given this as an example to study or to learn about fixed points analysis and so on. 1 minute. Okay, yeah. So the simpler, the system that we will study is what is known as a non-uniform oscillator. Okay, this has nothing to do with synchronization. It's a model nonlinear system that you find in standard textbooks on nonlinear dynamics, most notably in the textbook by Strogatz. So what's a uniform oscillator? So this is a uniform oscillator, a limit cycle oscillator, where theta changes uniformly as a function of time. So a non-uniform would mean that you have to bring in some term here that doesn't allow theta to change uniformly in time. It has nothing to do with synchronization. This is just one guy, okay, some angle theta that lies between 0 and 2 pi, and the equation of motion is like this. As such, this has nothing to do with that. Okay, there is no coupling. There is just one oscillator. Okay. Okay, and let's say omega is greater than 0 and A is also greater than equal to 0. Okay. So let's just plot this function. Huh. So there's a question? Huh? Huh? We'll see. Because, as you tune A, some magic will happen. So I want to see that magic to happen. Okay. So this is, I want to plot this function, this one as a function of theta. Let's consider the case A greater than omega. Okay. So what is this function going to be like? See, minus A sine theta, okay, A sine theta we know how it like, it looks like this. So minus A sine theta will be like this. Okay. And what does this, so this is minus A sine theta, and what this omega guy does is it just translates it in the vertical direction, right? So therefore, if A is larger than omega, then of course the curve will be, it will not just, if I just plot it this way. So did I do it this? Okay, it will look like this. So I guess, let me see. So did I do it right? I seem to have it this way. Just omega minus A when theta, so yeah, okay, so I'm plotting it between minus pi and pi. But it's okay, if you can plot it between 0 and 2 pi, it just shifts that way. Right, I mean, did I do it right? I mean, let me see, when theta is equal to 0, so then this term is 0, so this term is omega. So I guess this term is, this is, 1 minute. A is less than, sorry, yeah. Omega is larger than A. Yeah, sorry. Okay, so this is the curve when omega is larger than A. The second one is, so what happens is, let me do the following thing, which is omega larger. Yeah. So let me, larger. So there are these three cases, okay? So this is omega larger than A, omega equal to A, and there will be the last case which is omega smaller than A. So let's do the following. So what I can do is that I can keep my omega fixed and tune A, okay? So what I do is that when A is very small, then omega is larger than A, then the curve is like this. Then I keep increasing A. At some point A becomes equal to omega, and this is this. And then at some point A becomes larger than omega, which is this, okay? So as you can imagine, I mean, if you increase omega, if you increase A, then this curve, it will come and it would hit the x-axis, okay? This is 0 minus pi pi. And then if you keep increasing A, then what will happen is that this curve will and do like this. Fine? I hope I did it right. Yeah, I think so. See here, is there a point, is there a value of theta at which d theta dt can ever become 0? No. Okay. What will happen is that d theta dt will be very close to 0, or let's say we'll take up a small value here. Here it will take a large value. So what will happen is that as theta changes over 0 to 2 pi, there are places, there are theta values, most notably let's say theta equal to pi by 2, where the particle will, where this guy theta will slow down a little bit, and there is a point minus pi by 2 where it would move fast. Okay, so it's like zap and then slow, something like that, right? This is what is happening. Here, is there a point, is there a value of theta at which d theta dt becomes equal to 0? Yes, which is this point, right? There is one point at which d theta dt becomes equal to 0. So therefore, this particle or this oscillator, it momentarily comes to a standstill at that theta value. And then of course, it cannot just stay there, because a slight perturbation will take it away. I'll come to the form of the. And here there are two such points. There is one point here and one point here. These are two theta values at which d theta dt becomes equal to 0. But then let's see, exactly at this point d theta dt is equal to 0. But what happens if d theta dt is slightly larger? That is, when you are slightly away from this fixed point. So by the way, these are called what are known as fixed points. So of course, I mean, in the notes I have given some tutorial lessons on fixed points. So fixed points are basically values of theta for which d theta dt is equal to 0. These are values for which if you start the dynamics exactly from those values, there is no motion. Okay? These are known as fixed points. Sometimes they are also referred to as equilibrium points, but this equilibrium has nothing to do with statistical equilibrium, because there is just one oscillator, so nothing to do with it. So let me just fixed points would be value of theta such that d theta dt equal to 0. Let's say if theta star is a fixed point, then it satisfies this equation. That is to say that, this would mean that omega minus a sine theta star equal to 0. For example, here there is no fixed point, here there is one fixed point, and here there are two fixed points. But let's see what happens. Can somebody tell me what happens if I start exactly at this fixed point, then there is no motion. But if I if I initiate my dynamic slightly to the right of this point, then what is going to happen? D theta dt does what? D theta dt is increasing, right? So what it will do is that it will push the system away from the fixed point, right? And what happens if you are on this side, if you are to the left of this one, then what happens? Sorry. So this side d theta dt is negative, right? Because so d theta dt is decreasing, not negative, it is decreasing. So therefore this side it will be pushed towards it. So therefore this becomes what is known as a half stable fixed point, right? Why it is half stable? Because if you are there, then theta would tend to increase, and if you are there, then theta would tend to decrease. Because d theta dt is decreasing here, it is increasing there. Okay? So therefore, if you start your dynamic somewhere here, you will be pushed towards this point. If you start your dynamic somewhere there, you will be pushed outward. What happens if you do here? Can somebody tell me? What is the nature of this fixed point and this fixed point? So this one, it will be pushed towards it, but this one, it is negative also, it would be pushed towards it. So this becomes a stable fixed point, and this becomes an unstable fixed point. Right? Fine. So what happens is that this is the phenomenon of bifurcation, that you are given a nonlinear differential equation and there is a parameter in this equation of motion, namely the parameter A. And as I tune that parameter A, the nature of the solution changes. Why is this fixed point important? Because in the long time limit, if you run the dynamics for a very long time, then the system would eventually settle down into the stable fixed point. That's what we saw in the case of limit cycle, no? That whatever you start out from in the long time limit, the system would settle into a limit cycle. Here, instead of having a limit cycle, you have a fixed point. So if you are somewhere here, if you run the dynamics for a very long time, you would be pulled into this point. If you are here, you would be pulled into this point. So this stable fixed point is going to give you the long time dynamics of the system. Here it is an half stable, and here there is no, here there is no fixed point. Okay. So that is the utility of the fixed point, and one can find out the equation of the equation determining the fixed points. I mean that I had assigned as a so let me just write it down here. So when A is less than omega, then there is no fixed point. When A is equal to omega, then you have a half stable fixed point. Half stable fixed point at theta equal to pi by 2. This is theta equal to pi by 2, yeah, because it was here. And then, so this is case 1, this is case 2, this is case 3. And the case 3 is when A is larger than omega or omega smaller than A here. Then there are two fixed points, a stable and an unstable. So it seems as though this half stable fixed point, this point was half stable. So it splits into a stable and an unstable fixed point. There was nothing here, no fixed point to start out with. You keep increasing A, suddenly a half stable fixed point emerges that splits into a stable and an unstable. Or if you go in this direction, these two guys, they say, you can think of it like the fixed points that are colliding. So the half stable, the unstable and the stable fixed points, they collide, form one, and then they eventually disappear. They annihilate each other. Okay, so the fixed points, you can check that the fixed points which I denote by theta omega, this satisfies this equation, sine inverse of omega by A. And of course, I mean there will be two such values, because if I solve this equation, this equal to 0, then you get theta to be equal to sine inverse of omega by A, but then there are two such points. I mean, why will I get two such points? I mean, a solution of that equation. If I solve this equation, then I get sine theta star that is equal to omega by A, or theta star is equal to sine inverse of omega by A. But I am claiming that this gives rise to two solutions. There are two possible solutions. Both will satisfy this condition. So why there are two such solutions? Why this doesn't determine theta star uniquely? This equation, I claim that it doesn't determine theta star uniquely. Yeah, no, because it is giving me the sine theta star, but cosine also will matter. No, cosine can be positive and negative. So therefore, one term will come with cosine positive and another with cosine negative. And the one with the cosine positive is the one which is stable. You can just check it. And so cosine of theta omega, this is equal to, so what would be cosine of theta omega? If theta omega is this, what would be cosine of theta omega? And A is larger than omega, so I am fine. This is the real quantity. Why do I? Yeah, yeah, sure. Which point? This one is stable? Okay. Let me draw it big. Okay, something like this. It's not very symmetric, but okay, you understand what it is. Okay, so this is a fixed point, this is a fixed point. You understand why do I call it fixed point? It's fixed point because if you start from the, if you initiate your dynamics from these points, you are stuck. You cannot move out of it. Now this one, what happens if I start from a theta value which is slightly to the left of it? Then you see d theta dt is decreasing in this direction, right? Look at d theta dt, no? The d theta dt value that you have here and the d theta dt value that you have here, definitely this value is larger than this value. So d theta dt is decreasing. So theta would like to decrease in time. Okay, so if I start from here, so what it would do is that, I mean, because the velocity is this way, it would try to pull it this way. And here it is negative, so it would pull it this way. Okay, so this becomes stable and this becomes unstable because it is increasing and decreasing and so on. Negative and so on. Okay, this is positive. Why do I do this problem? Because we will see that this one, it can be couched in this form through some transformation that I will talk about later. Huh. Yeah, please. Huh. This one? Yeah, okay. So what is the solution? Okay, so let's see. What is the definition of a fixed point? This was my equation. Okay. Okay. So fixed point means a particular value of theta, theta star or theta, I was using theta star or theta omega, which is such that d theta dt evaluated at that value of theta is 0. So therefore, omega minus a sine theta omega, this is equal to 0. So if I solve it, I get theta omega is equal to sine inverse of omega by a. But then there can be two such solutions. One is this, given this sine inverse, so cos theta omega can have either a plus sign or a minus sign. So 1 minus omega square by a square. Clearly you see that if omega is larger than a, then you cannot solve this equation because sine lies between minus 1 and 1. That is the reason why in the first case you did not have any fixed point to start out with. Right, because we saw that in one case you don't have any fixed point, you had a situation like this. Why? Because you don't have any solution of this equation. Or you can look at it from here also, that if omega is larger than a, so then it's a square root of a negative number. Yes, exactly. So that is the half stable one. So half stable one, the problem is that if omega is equal to a, but then how do you know that it is half stable? So you have to go, by the way, there is a formal way to decide on the stability of a fixed point. You have to linearize the equation about the fixed point. It is also given in the notes, and I have also given some exercises to tell you how to do linearization. And if you are, at a point at which linearization doesn't work, then you have to go to the next order, like non-linear analysis. But at least, because I don't want to teach linear stability here, but at least physically you understand, no, that either you have this bottom point touching the x-axis or not touching the x-axis. Okay? If it touches the x-axis, then you have a half stable fixed point, and then it goes below, and then that half stable fixed point splits into a stable and an unstable fixed point, or when it is high up, as it is here, there is no fixed point. Yes, exactly. Okay, okay, so that is a pedantic point. Okay, so you say that okay, if A is non-zero, okay, I don't. So let me put it this way, that uniform is a special case of non-uniform. In that sense, okay. But you understand why it is called non-uniform, because the velocity doesn't change uniformly, as a function of theta. There are some theta values at which it speeds up, and there are other theta values at which it slows down. This is nothing to do with limit cycle. Why did I study this problem, bring up this problem? Because I will show that this analysis helps in solving this equation. It has similar form, excepting that here there is no summation. Here there is, a beast like a summation over n variables sitting there. So we'll see how to do it. So now we come to the Kuramoto model and try to see what we can do with it. So let me just keep this guy here because I would need this. So this. And please remember that solving this equation is not an easy job, and the way Kuramoto did was really something very original and very, it was something that people had not thought about earlier, and partly that explains his winning the Boltzmann medal. Although I guess the citation doesn't say, the citation hasn't yet been put up, I think. Okay, so let's just try to come back to the Kuramoto model and see what I can. 1 minute. In the meantime, you can think about questions to ask me. So. Okay. Okay, fine. Now I'll introduce several notions today in the context of the Kuramoto model. So therefore, let me start from here. First of all, let's make an idea of what sort of, what values of n we are interested in. See, we want to see synchronization in a large collection of oscillators, not like synchronization between two oscillators or 5 or 7. Okay? So the first one, because what is it that we want to do? The ideal thing would be to know, for example, in the context of this cardiac muscles, whether you get synchronization and all, and that is not constituted by 1 or 2 oscillators, but a whole bunch of them. So let's take n to be much larger than 1. Okay, that's the first thing. The second thing to realize is that how many frequencies are there. So this is a set of frequencies. So how many frequencies are there? There are n such frequencies. Okay, and if you have a long list of real numbers, what's the first thing that you do? How do you visualize them? Do you suppose you are given 500 real numbers? Do you look at the data? Do you go through the individual entries and decide on something, or you do something better? Histogram, right? So therefore, if n is much larger than 1 and have a whole bunch of these real numbers, then the first thing that I would do is to define a histogram or a probability distribution. They mean the same. If n is large enough, then this histogram will be replaced by a continuous function. So this g of omega, it may have any shape that you feel like. For example, g omega could be a Gaussian to the power minus omega naught whole square by 2 sigma square root of 2 pi sigma square, whatever. It is in your hand. It could even be Lorentzian or whatever. Okay. So these frequencies, they are changing from one oscillator to another. Now oscillator number 5 has got its frequency which is 56 hertz, as opposed to oscillator number 76 whose frequency is minus 282.56 hertz. Okay? So therefore the frequency value is changing from one oscillator to another, but the thing to note is that these frequency values are time independent. Why? Because these frequency values, if you recall, they characterize the frequencies of the underlying limit cycles. So they don't change as a function of time, right? And they are random in the sense that this frequency doesn't take up the same value for every oscillator. For every oscillator, it's a different number. It's a different number, but then the numbers are time independent. If I am red in color and indeed I am wearing a red sweater, let's say red is equivalent to 10 hertz. So I'll keep wearing a red sweater throughout the lecture. So therefore my frequency value is not changing as a function of time. So therefore these frequencies, they are called a source of quenched disorder. Why disorder? Because it is changing from one oscillator to another, and quenched meaning that their values don't change as a function of time. If I draw the histogram now and if I draw the histogram 10 minutes later and I draw the histogram 15 minutes later, I get the same function, whatever that function is. Okay? So these frequencies, they constitute a source of quenched disorder in the system. What is the other source of disorder that we can think of? And eventually we will study that system. Maybe I keep it, okay? You all seem to be familiar with Langevin equation, no? At least a fair number of raised hands I remember from the first lecture. Okay? So what is the other source of disorder you may have is you may have a noise term here, okay? Like again, noise meaning that it is different for different oscillators. So I may have another term here which is also different for different oscillators, excepting that instead of being time independent, it depends explicitly on time. I may have another source of disorder of this sort. But here the difference is that although the number is varying from one oscillator to another, not just that, for the same oscillator, eta takes up different value at different times. In fact, in the Langevin equation setting, what you do is that you take this eta it to be a Gaussian white noise. You take its average to be equal to 0, and so those of you who don't appreciate it, I mean, you can forget about it because we will anyways come back to it later. This is largely for those who said you know. So to discover that you know, you can look at it to say, oh, I know this. Okay, so this is a noise which is again different for different oscillators, but it is changing as a function of time. So such a source of noise is known as annealed disorder. So these are largely the two classes of disorder that you can think of. One that is time independent or quenched, that is this one, omega I, and the other that is changing as a function of time. At any given instant it is disorder, it is a source of disorder in the sense that for different oscillator eta has got a different value. But then it is not time independent, it is time dependent. It is changing as a function of time. Okay? So at the moment we are dealing with only this quenched disorder because we don't have this term, but let's say on Friday probably I'll start with the version of the Kuramoto model in which you also have this source of disorder, and then we will see an interesting interplay between quenched disorder and annealed disorder. Is this definition clear? What is quenched and what is annealed? Quenched is time independent, annealed is not time independent, time dependent. So this quenched disorder, it is typically very difficult to deal with in analysis because one which is red in color retains its color, and here eta it continuously changes. So red becomes blue, becomes yellow, becomes green, and so on. This one. Okay. So this is okay, right? This so you should say something because I am not able to read your mind. Huh? You get it. Okay, so you say that you get it. So then I get it. Huh? Otherwise I don't get it. Huh? Huh? Ah, yes. Sorry, at a given time? No, see, these are frequencies of the underlying limit cycles. Every limit cycle has got its own intrinsic frequency. I cannot play with it. What I can play with is the observed frequency, not the intrinsic frequency. I am given a bunch of limit cycles. Every limit cycle has got its own frequency. I cannot do anything with it. I cannot tamper, with the dynamics and say that. Then it's a different system. I am given 50 van der Pol oscillators. Each one has got its own limit cycle, its own frequency. I cannot do anything with that. What I can do is that I can change the collective dynamics in such a way that the observed frequency is different. D theta dt equal to omega is the defining equation of one limit cycle, and there are many one of them, and so therefore each one has got a different this thing. If not clear, then we can continue, but not now, after the class. Okay. So this is the third point is, how am I going to visualize synchronization in this system? So what I told you yesterday is that synchronization would mean a state in which the phases change in time, maintaining a constant phase difference. Okay. See, you cannot stop the phases from changing in time. Okay. They have to change in time, but then unless you are at a fixed point, you are exactly at a fixed point. So synchronization would mean that the phases change in time, maintaining a constant phase difference. So how do I visualize synchronization in this system? So it is done in the following way. So what you do is that, let's say at time t, what you do is that you have your n oscillators. Okay, you have your n oscillators. So therefore you have n theta i's. Okay. So what you do is that each theta I lies between 0 and 2 pi or minus pi and pi, it does not matter, it is the same thing. So you represent each theta I by a point on a unit circle. So there will be n such points. So what you do is that, suppose you are doing a numerical integration of the dynamics. So what you do is that you just integrate these equations of motion, and at any time t, you collect the values of the different phases and you prepare a list of those theta values and you represent them on a circle. Then what you can do is that you can define this guy, or okay, let me see. So this is a unit circle. So what I can do is that I can define these vectors. These vectors, they connect these individual points from the center of the circle. And then what I can do is that I can take a vector sum of all these vectors. Okay. So I end up defining a quantity which is, or let me put it this way. Let me see how the notation that I am using. Okay. So what I can do is that I can draw these vectors, and then I can find the vector sum. So what I will find is that, so let me see. So let's say this is the vector Ri t. So what I can do is that I can take the vector sum of all the vectors and divide by n. Why do I do it? I do it because suppose these points are uniformly distributed over the whole circle, okay? and I have a large number of such vectors. So they are just uniformly, these points are uniformly spread out on the circle. That is to say that this Ri vector can point either this direction, in this direction, or this one, or this one, or this one. All directions are equally likely. Then what am I going to get if I do the vector sum? If I do a sum of a large number of vectors, each one is randomly oriented over the angular range 0 to 2 pi, what am I going to get for this vector? 0, right? And if it so happens that a number of these points, okay, there are a few outliers, but let's say a number of these points are together. Of course, there are some points which are away, because this is also a possibility, no? Then if I do a vector sum of all these vectors, then what am I going to get for the vector sum? A non-zero number. Why do I get a 0 here physically? Huh? Yeah, because what is happening is that n is very large and they are randomly oriented. So for every vector pointing this way, there is another vector pointing that way. With a very high chance you find another one pointing this way. So they just cancel. But here no such cancellation is going to happen, because let's say the points are kind of close together, then you are going to get a value of this, this vector will not have 0 magnitude. It will have a non-zero magnitude. So instead of writing it as a vector, since I am on a unit circle, I write it this way in terms of a magnitude and a phase, which is the same thing. I guess you know this from complex analysis, that this is a vector in 2 dimension unit circle. So I can write this as e to the power I theta j. This you know, right? Because in 2 dimension you can define a vector in terms of 2 components, cosine theta and sine theta, right? And then you can combine the 2 as cosine theta plus I sine theta, which is e to the I theta, right? This is just pure complex analysis. So in this language, what it would mean is that if theta j's are uniformly distributed in 0 and 2 pi, then e to the I theta j will have the values plus 1 and minus 1 with equal probability. E to the I theta j will have values either plus 1 and minus 1 with equal probability magnitude wise, and then the sum will give you 0, but otherwise you are going to get a non-zero value. So what is this psi in terms of this thing? So psi would mean this r of t, or this r of t, this is the resultant vector. I don't have any other colored chalk. Okay, doesn't matter. So let's say here the resultant vector would be somewhere here. Okay, so this vector has a magnitude r of t, and psi of t would be what? It would be the orientation of the resultant vector, the angle, right? Because these are many vectors, you take the sum, you get a resultant vector. The length of that resultant vector will be r of t, and the orientation of that resultant vector would be psi of t. This is fine. I mean, this is just complex analysis. This is not why Kuramoto was given Boltzmann medal. Is this okay? This is just a way to visualize the system. Okay. By the way, this one eventually we will call it the order parameter of the system. Why do I call it order parameter? Because if r of t is equal to 0, then I would say the system is unsynchronized. R of t is equal to 0, let's say for all times. So the points are just moving around, there is no question of the points maintaining a constant phase difference, then r of t would be 0. At any instant of time I go and measure r of t, I am going to get 0. So I will say that the system is not synchronized. While if it so happens that there is a cluster that forms, cluster of points that forms, and if each point moves in time maintaining a constant phase difference, so this cluster will just keep rotating like this. So at any instant of time, if I compute the vector sum, I am going to get a non-zero value for the length of the vector. Of course the angle will change, but the length of the vector will be non-zero, right. So therefore when r of t lies between 0 and 1, we say that the system is synchronized. So I will soon ask you a question, but before that tell me if this definition is understandable or not. So R of t gives you a macroscopic observable, an observable that relates to the full collection of oscillators that allows you to distinguish whether this, make a distinction between the synchronized state of the system and the unsynchronized state of the system. So therefore, let us say in simulations, what I can do is that at any instant of time I can compute this quantity, and if I get 0, I say the system is unsynchronized. If I get a value, by the way, this r of t can, the length of the vector can at most be 1, right, because I am on a unit circle. So it can be at most 1, and the smallest value that it can take up is 0. It cannot be negative, right, because it is a length of a vector. A length of a vector cannot be negative. So when it is between 0 and 1, we call it synchronized, and r of t equal to 1 is extreme synchrony, like the maximum synchrony that you can have in the system. And r of t equal to 0 is when the system is unsynchronized. Huh? Huh? Uh-huh. You mean that a cluster here and a cluster there, something like that? Okay, you can have it, but what we will see is that the kind of sign term that we have, no, it doesn't allow 2 clusters. It always forms 1 cluster. If you have sine 2 theta, then you will have 2 clusters. And this has to do with the fact, and that is the reason why I did this this thing, because this has just 1 stable fixed point. It doesn't have 2 stable fixed points. If you do sine 2 theta, then it will emerge. But yeah, in principle, yes. So the main point is that, okay, so let me put it this way, that if the points are randomly spread out in 0 to 2 pi, then you are getting a 0 value for the order parameter, otherwise you will get a non-zero value. So therefore, this r of t, it allows you to distinguish between a synchronized state and an unsynchronized state. And by the way, in order to have an r of t, which is r of t magnitude, let's say, let's look at this one, r of t magnitude that is non-zero, can you tell me, n is large, n is much larger than 1, can you tell me, do you need 1 or 2 or 5 or 10% of the oscillators to be synchronized, or a macroscopic fraction? A macroscopic fraction, right, because there is 1 over n here. So if there are just 2 or 3 oscillators which are synchronized, divided by n will not count. So you need a large number, a macroscopic fraction. In fact, number is not the right quantity to talk about, a macroscopic fraction of the oscillators to be synchronized in order to get a synchronized stationary state. So this r of t, this is called the order parameter of the system. How many of you have heard the word order parameter? It's a word borrowed from statistical mechanics. It's phase transitions, you talk about order parameter. Okay, so what does order parameter do? What does order parameter do? It allows you to distinguish between an ordered phase and a disordered phase. So this unsynchronized state, this is a disordered phase. This disorder has nothing to do with quench disorder or annealed disorder. It just means that there is no order, there is no macroscopic order in the system. The oscillators are doing whatever they feel like, they just don't want to be friends with each other. So that's why the system is disordered, and this is ordered because they have decided to go all together. Or let's say a good number of them have decided to go together, not all. Okay? There are some outliers, some who still would not like to make friends with others, but let's say a good number have decided to. Okay? So why do I introduce this order parameter? First of all, this allows you to distinguish between an ordered and a disordered phase, but even more than that, it allows you to write this equation in a much simpler manner. Okay? So let me just keep this definition here, and let's see how I can rewrite the equation of motion in a simpler. Before I move away, This definition is clear, right? That for,
So I was asking, like, this is for in-phase synchronization. I can understand that there will be like less than 1, but greater than 0 R value. But for out-of-phase synchronization, what value does it obtain?
this one will not be able to, this one would just, this R of t, it would just make out whether the points are uniformly spread out or they are clustered.
So I was considering this out-of-phase kind of, I mean, from auto model and every model.
No, it could be that what you are asking is you are going this way or that way. See, this you are measuring at every time instant. So if they go in the other directions, it will fluctuate. I mean, R of t will, the value will decrease. It will have a non-zero value. If a macroscopic fraction are kind of together, they go this way, but then yet they, they remain within a club, a cluster. I mean, rearrangement within a cluster is okay. So long as there is a cluster that is going around. Yeah, they may just go within this one. So why do I do this one? Because it allows you to rewrite the equation of motion in a much simpler manner. And in fact, this was the great insight which was, so let's just write this equation of motion, just write it out fully. If I just write it out fully, then what I get is k of sine theta j summation over j equal to 1 to n divided by n times cosine theta I. I am just expanding out the interaction term here. Sine theta j cosine theta I minus cosine theta j but then if I look at this equation, cosine theta j will be what? Summation over cosine theta j, j equal to 1 to n, 1 over n, what would it be? R cosine psi theta, right? If I do the real part of it, what do I get? R cosine sine theta, R cosine psi t is equal to 1 over n, summation j equal to 1 to n cosine theta j. So therefore this equation simply writes as omega I plus R of t sine do I need to do it? I guess this is too trivial to do it. I mean, I will feel very embarrassed. So tell me if you want to make me feel embarrassed. There is a question. This is okay because sine theta j, this summation is what? Sine theta j, that would be RT sine psi t. So I get RT sine psi t cosine theta I minus RT cos psi sine theta I, which I can combine into just one equation. Now you seem to see why did I do that particular model, because things look quite similar excepting for a sign here and so on, but things start to look similar. So this equation, it has a deceptive look. First of all, in this form, it seems as though the oscillators have become decoupled. Why do I say that from this equation it seems as though the oscillators have become decoupled? Because on the left hand side I have I, and on the right hand side also I have only I. J has disappeared. So it seems as though I can study this model for I equal to 5 and I equal to 7 and I equal to 15 and so on. So I can just independently, I can assign one of you to solve the equation of motion for I equal to 1, another one for I equal to 5, and that's it. I mean, you do. But it is only, it is very deceptive because you see, although it seems as though the oscillators have become decoupled, but actually they aren't decoupled. Why they aren't decoupled? Which term in this equation of motion tells me that the oscillators are not decoupled? R of t, right? R of t and psi of t, they depend on all the oscillators. Okay. So this sort of dynamics where there is one global field, one field, one term that relates to the whole collection of oscillators, one master term that relates to the whole collection which is determining the dynamics of the individual oscillators. This sort of dynamics is what is known as a mean field system. How many of you have done mean field approximation in statistical mechanics, right? Mean field Curie-Weiss model, you do exactly the same, right? When there is all-to-all coupling, so what you do is that you rewrite your equation of motion in terms of a single particle or a single spin which is moving in a mean field produced by all the particles. In the same way, here every oscillator is, the dynamics of every oscillator is progressing in a mean field R of t and psi of t produced by the whole collection. Let me just point out one thing, that you could do this, you could rewrite this equation of motion in terms of these mean fields, and this could be done only because I had something here that allowed me to do it. What was it? So every guy was interacting equally well with everyone else. If I had a term like this, that is to say that the interaction between the ith and the jth oscillator is sine of this divided by the separation between the oscillators. By the way, before I come to that, the way, okay, let me forget about this one first. Can I endow the system with a lattice structure here? This one. What defines a lattice? What is it? I mean, what is it that tells you that this is 1D lattice or 2D lattice or 3D lattice and so on? Coordination number, nearest neighbors, right? But here, every guy has got the same number of neighbors, n. So this doesn't have any lattice structure. It's a globally coupled system. Everyone is interacting with everyone else. So how can you endow the system with a lattice structure? It's kind of a well-mixed collection, or I don't know what to say it, but it's neither 1D nor 2D, because in 1D you have two nearest neighbors, three, but here everyone has got the same number of neighbors. So it seems like it's a kind of, I don't know, a structure in which everyone is interacting with everyone else. But then if I have to bring in some, and so therefore there is no notion of distance here. Because why there is no notion of distance? Because you are interacting equally well with everyone. It's not that you are you can make out that, oh, that guy is very far and this guy is very close. No, everyone is as far and as close as anyone else. So this is a signature, or this is a feature of a mean field system, that in the case of mean field system you don't have an underlying lattice structure, you don't have a notion of distance. Everyone is as close and as far as anyone else. So in order to have a notion of a distance, you have to put them on a lattice. For example, if I put them on a 1D lattice, I say that I have a 1D lattice, let's say a ring, on every site of which there is an oscillator. And then I can talk about distance. Say, let's say the oscillator on the ith lattice site and the jth lattice site, they are interacting with a with an interaction that decays with the separation between the ith and the jth lattice site, like this. Okay, this is what is known as a power law interaction, long range interaction, and alpha equal to 0 is the extreme long range interaction, which is the mean field case, mean field interaction. In this case, you cannot write down this equation of motion in terms of that r of t and psi of t. Why? Because of this guy. It doesn't allow you, because you are not interacting equally well with everyone else. You are giving more weightage to those oscillators which are close by and less weightage to those which are far away. But in the mean field system, which is alpha equal to 0, you are giving equal weightage. So for those of you who are not getting the whole of it, so I would say, this is a topic in itself, mean field systems and so on. At least, you hear the keywords and then go back and find out what they are. Or you can catch me also. But let me not give an introduction to mean field systems in this course, because this would take away from the, take me away from the main topic of this. So this is a mean field system, and it is a feature of the mean field system that I am able to write down the equation of motion in terms of a mean field, r of t and psi of t, which I could not have done had I had a term of this sort, I minus j mod to the power alpha. Okay? Yeah. Yes, yes, sure. So therefore, we would like to now see how does this one, how can we solve this equation. First of all, let's see what do I mean by solving this equation. Like obviously, I don't want to, integrate this equation, because even if I want, I can't. So there is no point in wanting to even do that. So what is it that we want to know? We want to know if I run the dynamics for long enough time, if I run the dynamics for 10 days or maybe 1 hour, 10 days is too much, and I go to a state in which R becomes time independent, that is, I go to a stationary state of the system, R becomes time independent, psi becomes time independent, do I get a value of R which is larger than 0? That is to say, I run the dynamics for a very long time and I ask, in the stationary state of the system, is the system synchronized or unsynchronized? I don't ask it for small times. Why? Because I want to get to a state in which R of t, what will happen is that if you, let's say if you run the dynamics starting from some, it's best to draw some diagram, okay. So let's say I run the dynamics starting with some initial condition. So what would be the initial condition? I need to choose n values of theta, and I also need to choose n values of the frequencies, okay. But the frequency values I need to choose, do I need to choose only once, or do I need to keep choosing at every time instant? Only once, because these are quench disorder variables. So I need to choose these frequency values only once from the frequency distribution g of omega, and then I need to also choose an initial condition. Okay? So given an initial condition, there is an initial value of this order parameter. Okay? And then as the dynamics progresses, so this is t, let's say I start with an order parameter value which is 0.8, let's say. And of course, as the dynamics progresses, the theta values get updated, and if the theta values get updated, I should put a t here to be more precise, as the theta values get updated, so would the value of r and t, right? R and t also will change. So therefore this r of t, it will change as a function of time, it would do something. But then if it so happens that it gets to a time independent value at long times, a value which is greater than 0, then I will say that the system has synchronized in the long time limit. This is the stationary state of the system. But it doesn't have to be this way, it may as well go down all the way to 0. Then I will say that in the stationary state the system is unsynchronized. It may so happen that it can even go up and in the stationary state hit the maximum value of 1. Then also I will say that the system has become synchronized. You get this plot? You must have done this thing, right? I mean, seeing how does a quantity that depends on time change as a function of time. Now you may say, is it guaranteed that there will be a stationary state for any given dynamics? No, it is not guaranteed. You can only hope for it, okay? And in this case of the Kuramoto model, I think Kuramoto in those days in 84 or so had done some simulations to see that this is exactly what happens, that there is indeed a stationary state. Indeed R of t changes, but at some point doesn't any longer change and it settled to a time independent value. And I will be interested in this part of this dynamic. When R of t has attained a time independent value, stationary state. What sort of stationary states you must have encountered in your BSc, MSc courses, right? I mean, some stationary state? Equilibrium stationary state, right? Equilibrium when macroscopic observables don't change as a function of time. You have a time independent distribution of the microstates and so on, right? So therefore, we would like to know what is the value of the, the value of the stationary R that the system settles into at long times. Huh. R equal to 0 is unsynchronized. R greater than 0, I will call it synchronized, maybe not fully synchronized, obviously, because if R is, let us say, 0.006, I will still call it, definitely it is not unsynchronized. Because I have to, a little synchronization, very little, but still, I mean, there is some. So I am interested in the stationary state of the system. So in the stationary state, what happens is that R and psi, they will become time independent. So therefore, in the stationary state, this equation rewrites as d theta I dt. This, of course, you cannot make theta I is not change in time. Theta is will change. These are dynamical variables. You cannot stop them from changing. So this becomes omega I. This anyways is time independent. Kr. But then in the stationary state, I can forget about the time dependence here and here. So fine. This is the stationary state dynamics. Can I make it even simpler? Is there something that I can do with this equation that would make this equation look like this guy? What is it that is preventing it from looking it like this guy? No, but omega is here, omega is here. Huh? Yes, exactly. Argument, there is a psi sitting here. If somehow I can kick it out, then sine of minus theta would be minus sine of theta and this would look like this. Can I kick this guy out? I can do a change of variable. Can I do the change of variable here? Why? Because here, so here what I have to do is that psi has become time independent, so I can measure my angle with respect to that psi. But here, I cannot do it because I have to keep rotating my frame. At every time instant, I have to redefine my 0 theta axis. But here I don't have to worry about this because psi has become time independent. So let's just do this, and so then this equation looks exactly like what I had written down for. Theta is still time dependent. So what? So that's the magic. Theta is have become, look at the magic of it. That R of t to the power I psi of t. Good question whether you asked it with the same intention as the one that I am trying to explain it with, that I don't know. Let me just. So I have gotten to a state in which psi has become time independent and R has become time independent. But theta is still time dependent. So what is happening is that you see this is a sum over many thetas. So thetas can organize themselves in such a way that this term is time dependent and yet the sum becomes time independent. Kind of magic, no? But actually it is not. I mean, like, if you have a sum of terms, let's say I say that there are 3 terms, let's say T1 plus T2 plus T3, and the sum is a constant 5. There are many possible solutions. I can say 1 plus 1 plus 3, or 4 plus 0 plus 1. So these can change as a function of time, and yet the sum is constant. The same thing is happening here. The thetas can happily change, and the way the thetas change is according to this equation or this equation, whichever you like, this one. The thetas are changing individually, yet the sum is giving me a time independent number. That's a feature of a stationary state, because it doesn't care about which oscillator is where. It just cares about the sum, and the sum has become time independent. So now we are in good shape, because now this one I don't need. This one looks exactly like this one. But then I don't know what, see here, the advantage is that I knew what A was. A was a number, it's a parameter that I had in my hand. Here, what is the value of R? I have to solve. To know R, I better know, okay, psi we have put equal to 0. See, to know R, the value of R, I better know the values of thetas. But to know the thetas, I need to know the value of R. I don't know what to do, because, I need to know thetas, but then to know how the thetas are changing, I need to know R. But then to know R, I need to know thetas. So they have to be found out self-consistently. Okay? And again, I emphasize that this is not a statistical mechanical system. You cannot, there is no noise here, this term doesn't derive from a potential, so you cannot say here that there are n oscillators and therefore P equilibrium of theta I is some e to the minus h by kBt, something like that you cannot say. There is no underlying Hamiltonian, there is no temperature. You cannot do standard thermodynamics also, because there is no entropy function to maximize, the free energy to minimize. It's a non-linear dynamical system. There is no noise here. In fact, it is a deterministic system. The only randomness that you have, okay, this is one source of randomness, which is quench disorder. But then the only randomness in the dynamics that you may have is because of your what? What can lead to some randomness, in the sense that at time t, I may have many different values of the thetas. If I happen to have many different values of thetas, whom am I going to hold as culprit? Who is to be blamed besides God? Who is to be blamed if I find at a later time t that I have many different possibilities for this set? There is no noise here, there is no eta here. So why, if at all, I will get different? See, this is because of what? Different, what will lead to different this? Initial condition, right? The only thing that is random or that may lead to some randomness is the initial condition. For the given set of oscillators with given frequencies, if you give me the initial condition, there is one and only one final condition. Only if I change the initial condition, I may get different. So let's see, how do I do this one? So this analysis is also not easy, but still. So again, Kuramoto's whole book is devoted to analyzing those equations, and I strongly urge you to read this review by Crawford, where he unveils a fascinating connection between this problem and the Landau damping problem in kinetic theory. Okay? On the face of it, oscillators have nothing to do with plasma, okay? But you get similar equations for kinetic theory if you do a kinetic theory. Okay, so let me see. Okay. So how do I need to solve for this R self-consistently. Okay. So let's see, how do I do it. So I will just spell out some of the basic steps, but leave out the integration to you, because even if you cannot do, Mathematica can. In either case, it is done. So therefore, I don't do it. Okay. So I have n much larger than 1. I need to know the thetas in the stationary state, and if I know the thetas in the stationary state, I know the value of r. Okay? So like again, I ask the following question that I have n real values of thetas. Then what's the first thing that I should do to characterize these theta values? I have a long list of theta values, 500 theta values. So what is the thing that I do? Histogram, right? So therefore I define a probability distribution or a histogram which is defined in the following way, that at time t, first of all what I do is that I can group the oscillators in terms of their frequencies, because these are quench disordered random variables. If a particular term doesn't appeal to you, let me know and I'll try to couch it in another language. Does this make sense? Group the oscillators, because you see every oscillator has got a particular value of frequency that is time independent. So I can say, okay, these are oscillators for whom the frequencies are between minus 1.5 and minus 1.52 hertz. So this is one group. So I prefer to call them as colors instead of frequencies, because that makes me easy to that makes it easy to talk about it. So there are red colored oscillators and blue colored oscillators and green colored oscillators and yellow and orange and this and that. Okay. So what I do is that I choose oscillators that have the same frequency omega, and I ask how many of them have the phase angle theta, or more precisely have the phase between theta and theta plus d theta at time t. Is the definition okay? So at time t I group the oscillators, and you see this grouping, do I have to group the oscillators at every time instant afresh? No, because the frequencies are time independent. So a red is a red and a blue is a blue. So at time t equal to 0, I may say, oh, these are the red oscillators, this is my group 1 and this is group 2 and this is group 3 and 4, and that's it. So given a frequency and a time instant, this gives me the fraction of the total number of oscillators that have got the angle theta at time t. So this is the probability, and therefore this guy is a probability density, or histogram. It's just a fraction of total number of oscillators. So what would be the normalization condition for this guy? What should I do? I should integrate over what? See, these are given to me. I am asking only for those oscillators that have got frequency omega at time t. What is the number, what is the fraction that have got the phase value equal to theta? D what? D theta, right? Because I am clubbing them, no? These are red color oscillators. Frequency I cannot integrate over. I have given them the frequency, so this is the and then in terms of that quantity, can I rewrite this guy? Let's see if I can rewrite that equation. Recall that here I am talking about the stationary value of r, so therefore I should talk about the stationary distribution. That is when the probability distribution becomes time independent, right? Because r of t, okay, maybe this is not obvious, so let me first write this down and then it will become clear, I think. Let me first write the time dependent part and then I guess the time independent part will be easy. This was the definition to start out with, right? Can I write this down not to distract you? Forget about it. Can I write this down in terms of this probability distribution? In the notes I'm using rho, okay. Let me write rho. Can I write this down in terms of rho? Some integral of rho, clubbing, etc. How? Who said yes? Whoever said yes said it with a lot of hesitation. So, yes.
We have to define what is the partition or the relation between a discrete partition for discrete j and the d theta. What
Yes.
is the relation? And then we replace with the integral.
So what I do is that, you see, this is a sum over all the thetas. So what I can do is that, let me first go to the group of oscillators with red color. Okay. So how many of them are there? Okay. So this is the fraction of the number of oscillators for which the phase value is theta. For them, the value of this e to the I theta would be just e to the power I theta, right? But then this is for only, this is the fraction of the total number of oscillators with frequency omega, this p theta d theta. For them the this one is this, but then how many such oscillators are there with frequency omega? It is g omega d omega. See, this one is you fix omega, then you get p theta d theta e to the power I theta. But g omega d omega will give me what is the total number of oscillators with frequency omega. And then I do two integration. One integration is over theta, one integration is over omega. Okay. So look at the way this guy is defined. Okay, let me. This is this one. It gives me the number of oscillators, fraction of the total number of oscillators with frequency omega. So this omega is given to me. So in that group, how many are there with angle theta? So, okay, so there are this group, okay, this is group, this is group. So these are the different groups, red, blue, yellow. So within red, these many have got the angle theta, for which the value of this function is e to the power I theta. And then I need to integrate over all possible value of theta within that group. This is this integral. But then now I need to take into account the contribution of the different groups, which is d omega d omega. Fine? Sorry, this is rho. My favorite symbol is P, but while writing down the notes, for some reason, I started using rho. But then, so therefore, I get this equation r of t to the power I psi of t is equal to d theta d omega g omega e to the I theta p of theta omega t. And in the stationary state, what happens? So this guy becomes r, time independent. Psi, we decided to put it to 0 in the stationary state. So this equal to d theta d omega g omega e to the I theta. But then this one has to be replaced by the corresponding stationary distribution. Why? Because stationary state is one in which r doesn't change, the sum doesn't change, which is to say that the histogram that you construct out of the thetas, that doesn't change its form. Yeah, that is what you do in equilibrium statistical mechanics also, no? P equilibrium theta e to the minus beta v theta. Okay? The probability distribution doesn't change its form, the probability distribution has taken up a time independent form. So I need to find this guy somehow. Psi we set it equal to 0 by rotating my axis. Because I am in the stationary state, it is a time independent quantity, so therefore I can rotate my axis and so on. By the way, so this part I will not do, but you in the notes you will find an explanation. I mean, just let's say, and this also gives me an opportunity to. Most of the time you are testing my knowledge, but I guess it is fine if I once in a while test your knowledge to know how much you know. Okay. So this P of theta omega t, if I have to write down a time evolution equation for this guy, what would it be? Can somebody make a guess? See, this is a, oh sorry, this is rho, sorry, again. Ah, gosh. Gosh. If I have to write down a time evolution equation for this guy, how does the histogram change as a function of time? Of course, eventually it gets to a time independent form. The time independent form of the distribution is this one. But the time dependent form, if I need to write down the evolution equation, how would it look like? Let me give you some hint. Would you like to have some hint? Continuity equation, absolutely. It will be a continuity equation. Why? Because see, continuity equation emerges when there is some conservation. What is conserved here? Number of oscillators with a given frequency. Because you see, rho, it takes care of the club, no, the frequency club. See, the number of red colored oscillators remains the same all through the evolution. Green, of course, the total number of oscillators is a global constraint, that's fine, but locally also, for every frequency, there is a given number of oscillators that's conserved as a function of time. So, just as you know that this equation, how many of you do not know about equation of continuity? And then I'll stop here. Let me first get the answer. Equation of continuity, how many of you know about it? Don't know about it. Oh, no, don't know is better, okay. Okay, so almost all of you would know. So an equation of continuity is an equation of the following sort. That did you learn in which course? Because it appears in every course more or less, foundational course. It appears in electrodynamics, it appears in statistical mechanics, it appears in quantum mechanics, which is your favorite topic. Because everybody raised their hand on this, okay. So this has this particular form. Okay, so where J is nothing but x dot times P. So here also it has the following form, minus del theta of J, which is the probability current. I'll stop here. So J of theta t will be what? It would be theta dot times rho of theta omega t. But I want to scare you a little bit, and therefore let me just write down this equation. You will see what a horrible equation this is. What is theta t? Theta dot is what? Theta dot is omega minus kr sine theta, theta I omega I. From there, if you want to know what is theta, you write down the equation for r. So this would be omega minus k. Let me just write it down because I. So this is the theta dot that you have to put in here. So theta dot is the velocity. Those of you who know what the velocity, what the form of the equation of continuity is, the current is always density times velocity. And what is the velocity? Velocity is this one in discrete, when I'm talking about large n, I better replace r by the formula that I had written down in terms of the integral, which is, it appeared somewhere. But just convince yourself that this is the equation that you get. There is no No, no, there is omega dependence which is coming here. Yeah, because this is the interaction term. So the interaction term is what? If I write it out fully, the interaction term was k by n summation sine of theta j minus theta I. Okay, so the frequency term is there, and this interaction term I am just rewriting in terms of an integral. So this is a horribly complicated integro differential equation. So it's a differential equation in which one term involves an integral. So it's called an integro differential equation, and I have to somehow find the stationary solution of this equation, which is to say somehow set the left hand side to 0 and get the. So maybe it is too much. So I urge you to look up the notes and see if you understand. I have given some derivation of how do you get it, and then we'll take it up from here to see how do you get the stationary state and so on. Huh. Where? Here? No, no, no. This is this omega is fixed. You are asking how many of the oscillators have got the frequency omega. 1 minute. Yeah, yeah, yeah. Sure, sure, sure. Yeah, yeah. Okay. Yeah, yeah. Fine.